Hey everybody, welcome to the central limit theorem lesson. And the central limit theorem looks a little confusing at first, but it's really just building off of what we previously know. And what this is going to be doing is looking at sample sizes. And what we're going to do is create a sample mean and a sample standard deviation, and then our same normal distribution properties will still hold. And let me just show you how this works. So here we're back to our Plinko example, and I can just run this. Oh, that's boring. Let's run it like that. So I'll do a small one, 200 and about 250. Well, look at that distribution. It's actually pretty good. I can compare it to the ideal. That's how it should look in the long run. It's already pretty close to a normal distribution. And if we keep on running this, maybe I'll do a really small sample. There's a small sample. You can see the smaller the sample, it's not as close to a normal distribution. I'll do a really small sample. There's a really small sample, 18. Obviously, it's not even going to have enough data points. So the point is, the more data we have, the closer we're going to get to a normal distribution. Well, that one started off weird. Let's see if it will come back into our normal distribution. There's the middle catching up. So the longer this goes on for, the closer it gets to a normal distribution. I can put the ideal on. The ideal is where it should show up, where mathematically speaking, those bars should all level out. If we do this long enough, they should land on that. Wow, look at the 7. It's doing really well. Let's see if probability takes over. There it goes, drops down a bit. Oh, look at this right side, almost perfect. So as you can see, as we get to be a very large sample, we get to be very close to our normal distribution. 5 is doing well. All right, you get the point. After a while, this will eventually back down. It's always kind of fun just to watch it. It's like, when will it back down? I don't know. But as the data set gets to be really large, it gets to be harder to make big changes. So the movements get to be smaller. Okay. So one of the things to notice is as we run through these sample sizes or run through these experiments, the size of our sample changes our standard deviation. See how we have a really small sample size? The standard deviation here is going to be really big because the data is really skewed about. But as we run through larger sample sizes, the standard deviation is going to get much smaller. So that's going to be a part of our calculation today, using this sample size. All right. So the standard deviations and sampling distributions. So we have standard deviations and sample means from our data set. Oh, I'm in the wrong slides. There we go. We want to be in this one. Okay. So here we go. So suppose we have a random variable with a distribution that may be known or it might be unknown. So it might be normal distribution, it might not be. We're going to use subscripts to label this. So once again, mu x, that little u, we call it mu x, Greek letter mu, lowercase mu. That's the mean. Sigma x, that's the standard deviation. So that's been the same as what we did before. And now we're going to draw a random sample of size n. N is going to be a number, 100, 200, 300, whatever. And as n increases, the random variable x, which consists of sample means, it's going to tend to be normally distributed, as we saw. And take notes. So we're going to say our variable is normally distributed. That's what that capital N stands for. The mu x, so the mean is going to stay the same. The only part that changes is this part right here. The standard deviation is going to be divided by the square root of the sample size. So if we have 100 pieces of data, we take the square root of 100, so that would be 10. So it's 1/10. The standard deviation is 1/10 of what it was. And so for that, you just take whatever the standard deviation is divided by the square root of the sample size. But if you wanted to, there are calculators you could use. Here's a calculator. You type in the mean, standard deviation, sample size, and calculate. And look, the mean is the same. And the standard deviation, they take the standard deviation divided by the square root of the sample size. So the square root of 25 is 5. So 5 divided by 5 is 1. So that's called the sample standard deviation. And then once we get that, we can go back to our normal distribution curve and calculate our probabilities. So here's an example of just rolling some dice. I'll let you kind of look at this, and we looked at that Plinko example. Here's another one showing that these go to a normal distribution curve as our sample size gets larger, which we showed. And then here's how to calculate this on the graphing calculator. If you want to study that, you can, but we're going to be using our calculator right here that we've been working on, this one. It's a little bit easier to use. All right. So here we go. Let's just look at an example because you might be a bit curious how this is going to work. So here we go. We have an unknown distribution. Once again, we don't know that it's normal. It could be any distribution actually, but we do know it has an average of 90 and a standard deviation of 15. Sample size, whenever we have a sample size, we're going to be using the central limit theorem. So sample size of n equals 25 are drawn randomly from the population. Find the probability of samples between 85 and 92. Okay, so the average is 90. All right, the mean of a sample, size 25. So we know our average is 90. Our standard deviation is 15, and n is 25. So we go to our formula. The average stays the same. To find the new standard, or to find the sample standard deviation, we take the old standard deviation, we divide it by the square root of the sample size. So the square root of 25, which is 5. So that's 15 divided by 5, which would be 3. So our sample standard deviation would be the number 3, and our mean is 90. So I could take that into my calculator here. Mean of 90, standard deviation of 3. We're trying to find the data between 85 and 92. So I go in here between 85 and 92. And we see a picture of it. There it is, between 85 and 92. So 0.6997, so about 70%. There we go, 0.6997. And there we go. Oops. So that's it. So it's all the same work that we've done before using our calculator. The only new part is this right here. Calculating this sample standard deviation is the only really new part. So take note, the central limit theorem works when we're using sample sizes of size n. All right, I'll make some more videos next.